Hi, today's session is about mysteries of universe. There are a lot of mysteries in universe. I'll be discussing about few significant ones which has kept the scientific community on edge. A lot of scientists are putting in a lot of efforts, but they are still mysteries. It is appearing to be very magical, bizarre, counterintuitive, illogical at times. So I'll be discussing about these important mysteries. I'll be discussing about dark matter. Dark matter is something which is responsible for the life we have. It's responsible for all the stellar structures in the universe we have. It's responsible for how these galaxies and clusters of galaxies and superclusters have formed. Without it, with just the normal matter, all this formation of stellar structures would not have been possible. The cosmos, the universe would not have been same without dark matter. And then I'll be discussing about dark energy, which is responsible for expansion of universe. There's expansion of universe happening right now, and the expansion has become faster. Basically, Big Bang, it is said that the Big Bang created the universe out of this speck of matter, which is much smaller than a subatomic particle. The universe that we see today has come out because of an exponential expansion. Nobody knows what triggered that expansion, but this Big Bang theory says that from the speck of matter, the whole universe which we see today is born. So it was born, and then later the galaxies formed, and because of this formation of these cosmic structures and the gravitational pull, slowly the expansion gradually slowed down. But then again, it has been observed that the universe is now again expanding faster. It is accelerating. So that's a big mystery, and it is said that the energy or the force which is responsible for the expansion of this universe is dark energy. And this dark matter, balance of this dark matter and dark energy is something which is responsible for the universe that we see today. If only dark matter was there, the stellar structure would have formed, but because of the gravitational pull between these stellar structures, gradually everything would have started coming together. There would have been a major collapse or a major crunch. So with just dark matter, the universe would have led to a collapse or a big crunch. And with just dark energy, which is like a repulsive gravity, which is responsible for the expansion of the universe which is happening. And as I said, it's accelerating. The universe would have ripped apart, the structures would not have been there. It would have not allowed any galaxies or any solar systems to form. So basically, it's a balance of dark matter and dark energy which is responsible for the universe that we have today. And we don't know how it is going to behave in future. Is the dark energy going to remain the same? It is going to become more powerful, or it is going to become less powerful, because we don't even know what is this dark energy. So I'll be discussing about this dark matter and dark energy in first part of the video, and then we'll create another video for covering the second part, which is quantum mechanics. So quantum mechanics is another thing which I was talking about, is a very bizarre or appears to be a very magical thing. It is the same quantum mechanics for which Einstein said that God doesn't play dice. Why he said that? Because quantum mechanics is basically the study of micro constituents of nature, the subatomic particles. Any macro object, any big object, big in the sense which is observable to us, whether it's a tennis ball or whether it is a table tennis ball, or it is us or any other large cosmic object like a planet or anything. We know all these things are made up of atoms. Atoms are made up of subatomic particles like electrons and protons and neutrons. And we will think that we are made up of these micro constituents. So obviously the behavior is going to be same. Whatever the micro behavior is going to be there, that is going to be extrapolated for the macro objects also. But that's not how the universe is working. The physics which the macro world follows is very different than what the micro world follows. We know that the macro world is very deterministic. If I'm going to kick a football, I know what is the trajectory it is going to take. I know what will be the velocity at t1, t2 time period, right? Where it is going to land, I know exactly what trajectory will be there based on what is the force applied and all that. So it is a very deterministic world. We know, like, if I'm accelerating a car, what velocity it will be after 10 seconds or after 1 minute, and if I'm decelerating, I know like when it is going to stop and all that. So it is very, very deterministic, and the Newtonian physics or the Einstein physics is based on that. Einstein did a very interesting addition to the gravitational theory, a brilliant addition, genius addition. Basically, he explained what is gravity. Actually, Newton gave all the mathematics surrounding the gravity, but he was not able to explain what is causing this pull, what is this force which is pulling the two objects together. So he was not able to explain what is the agent which is causing this attraction. Einstein explained that any mass or energy is going to curve the space-time. It is going to curve the space. Einstein, along with space, Einstein included time also as a dimension, so he called it space-time, x, y, z and t, so all these 4 dimensions. And he said that any mass or energy is going to curve the space-time. If the space is flat, and if you put some mass or energy on it, it's going to curve the space-time. More mass, more energy is going to curve it more. So that's why we say that around the black hole, because there's a tremendous amount of gravitational pull, it bends the space-time like anything, right? So this is what Einstein and Newton said, but that is very deterministic physics. We know what is going to happen with the macro objects, but the micro world doesn't follow the same logic. You cannot talk about the same thing for electron, that okay, I know the electron is here, after t1 time, after t2 time, it is going to be here or it's going to be here. Micro world is very probabilistic. It is probabilistic, it is not deterministic. We can give a probability that okay, this is a probability that it will be here, or this is a probability it is going to be here. So that's why it is something for which Einstein said that God doesn't play dice, right? It's not probability, it should not be probability based, but that's how quantum world, that's how the micro world works. That is what we understand today. We don't have any other explanation for it today, that it is magical, it is probability based. There are a lot of other phenomenon in quantum which I'll be discussing, like quantum entanglement, like if you entangle two particles, if you make them interact in a way, and if you keep one particle here and if you take another particle to even to Jupiter, to the edge of the universe, if we spin the particle here, the particle is also going to get the spin at the same time. It's not that light is going to carry some message which is the fastest carrier in the universe, and then it is going to give that message to that particle and then it is going to spin. It happened instantaneously, as if they are connected and it's a single system. Spin here, spinning together. So I'll be discussing about quantum entanglement. I'll be discussing about an interesting experiment, Young's experiment, double slit experiment, which also gives a lot of interesting aspects about the micro world. Like when we start observing, the behavior changes actually, which is a very strange thing, that you start observing a thing and the subatomic particle changes their behavior completely. So I'll be discussing this quantum part in the part 2 of the session, and in the part 1 I'll be covering dark matter and dark energy. So as I said, dark matter is responsible for the formation of all these stellar structures. Basically, the mass energy density of the universe. We take mass and energy as equivalent thing. I'm sure that most of us know that Einstein gave that famous equation E is equal to mc square. That mass can be converted to energy and energy can be converted to mass. So both of them are equivalent. Mass and energy are equivalent concepts. So 68% of the mass energy density of the universe is dark energy, which is this repulsive gravity which is expanding the universe. 27% is dark matter, which I said is responsible for formation of these stellar structures in the cosmos. And only 5% is atoms, the subatomic particles, which we think is making the whole universe. Actually, that is just 5%. So all the objects, even the large structures like the galaxies or us, or small objects that we see, which is made up of atoms and subatomic particles, all this constitute only 5% of mass energy density of the universe. So the stars are spinning in the galaxy, and the galaxy is, as I said, clusters of galaxies are there, which is made up of hundreds or thousands of galaxies. Then there are superclusters which are made up of hundreds of clusters. All this would not have been possible just with the normal matter, just with these atoms. Unless we put dark matter into equation, this dark matter about which we are in dark about, these galaxies, we cannot explain the spinning velocity of the stars in the galaxy, we cannot explain this formation of the clusters, formation of the superclusters. So we have to consider that this additional mass is there, otherwise we cannot explain. The stars would not have been spinning, they would have been flying apart. These clusters would not have been there, the galaxies would have been flying apart. So this all cannot be explained without considering the dark matter, which I said is the 27% of the mass energy density of the universe. So the another proof of the dark matter is, like Einstein said, that mass energy is going to curve the space-time, right? So any light which is coming is also have to travel through this curved path, right? If the space was flat, light would have been going straight. But if you curve the space-time, light also has to travel this curve. It also has to go into this curve and travel. And this bending of light is called gravitational lensing. So we are looking at it from the telescope side. So if we see this bending of light, it indicates that yes, some major mass or energy is there which is causing this bending of light. So without this dark matter, that much bending of light is not possible. So the light which is coming from behind or from the galaxies behind the dark matter, and we see this gravitational lensing. This effect is called gravitational lensing. That indicates that much mass is present there, and the normal matter cannot cause that much bending of light. So that's why this dark matter does exist. Now the question is, we don't know what is this matter. Why we don't know? Because it is invisible. It doesn't have any electromagnetic interaction. It doesn't interact with light. Only thing, as I said, it has this gravitational attraction and it bends the light because of that force, because of that gravitational force. But it doesn't absorb light, it doesn't emit light, it doesn't reflect light, right? So we cannot see that matter. That's why it has been called dark matter, because we are in dark about it. It is invisible. The right term would have been invisible matter, but it has become famous with the term dark matter. So now coming to like what is this dark matter? Because we cannot see, we don't know what it is. We just know it by the effect, the gravitational pull. The only thing it has shown to us is that yes, it causes this gravitational attraction. That is only behavior it has, same with the normal matter. Otherwise it's invisible, no interaction with light, as I said, and it doesn't show any other indications which can help us understand what it is comprised of. So the scientists are working in different directions. They are thinking that these are made up of light particles called axions, which are hypothetical particles. Then there's another theory, it is made up of particles called neutrinos, like particles like neutrinos. Neutrinos are also ghost-like particles. We call them ghost-like particles because there are millions passing through me right now, but there is no interaction. We don't see them. So, but they are very light particles. Initially, they were considered to be massless, but later it was found out that they do have a tiny mass, right? So there are different hypotheses. Scientists are working on different theories. They are also even working on a theory that the gravity works differently on small scale and gravity works differently on a large scale. But so far no proof is there for it. But definitely research is going on in that area. Then Stephen Hawking mentioned that this dark matter may be made up of primordial black holes from the early universe. The black holes formed from the early universe. The black holes are normally formed by the collapse of stars, but in the early universe there is no collapse happening. So these primordial black holes are basically highly dense region in the early universe which caused these primordial black holes to happen. So Stephen Hawking suggested that this dark matter may be made up of these early black holes, these micro black holes which were formed in the early part of the universe. There's a lot of research being done on that, in Hawaii. There's a group of scientists actually from India, Japan and America who did research to see whether that is the case. they looked at the light which was coming from Andromeda galaxies, right? So if there's a dark matter in between the Andromeda galaxy and us, the dark matter should cause these bending of light or this gravitational lensing, what we call, which Einstein talked about in the general theory of relativity. So they should have seen a lot of these micro lensing events in the night when we did this observation, right? But hardly any micro lensing was seen, and only one micro lensing event was seen. So that indicated that the dark matter is not made up of these primordial black holes. Anuprita More and other scientists which I talked about, like scientists from India, Japan and America, they did this observation and they came to this conclusion that maximum 1 to 2% of the dark matter may be made up of these PBHs, primordial black holes, but other is definitely not made up of these PBHs. So it's still a mystery. We still don't know what dark matter is made up of. There's a lot of experiments going on. There's an experiment called LUXZ, liquid underground xenon Zeppelin experiment. It's a LUX, or in short it is called LZ experiment, which is being carried out in South Dakota, in Sanford Fundamental Research Facility in South Dakota. So, and 1 mile under the ground, they are trying to, they have a detector, this liquid xenon detector, and they are trying to see if any interaction this xenon is going to happen with dark matter, and they can get some information up from that interaction. So, this LZ experiment, there are other experiments, like in Canada there's an experiment called SNO Lab, where also they have a silicon germanium detector underground, 2 kilometers underground, where this again they have this detector to detect dark matter. Basically, there are detectors underground because they want to filter out as much noise as possible. So the cosmic rays which are coming, or other particles which are coming, they're trying to filter out as much as they can, so that only less noise in terms of particles or rays are going down, and only that is going to make it easier to detect the dark matter. So I talked about this LZ experiment, SNO Lab experiment, then they are trying to create the dark matter also. They're trying to create the dark matter in the Large Hadron Collider. It's a Large Hadron Collider, which is a 27-kilometer long tunnel in Geneva, Switzerland, where they are smashing the subatomic particles at near light speed from both the directions. And they are trying to basically create the scenario which was there at the time of Big Bang. So at the time of the Big Bang, there were tremendous collisions happening at tremendous energy levels, and the matter was, new particles were created at that time, and even dark matter must have been created at that time. So this is called like a mini Big Bang machine. So they are smashing these particles, and they are trying to see if the dark matter is created. And using the conservation of momentum and conservation of energy, they will come to know if some change is there in the momentum or change is there in the energy levels. So LHC has had a couple of runs, and now third run is going to start, but so far no clue. There's no clue about dark matter. They have not seen any creation of the dark matter. So there are detectors trying to detect dark matter. There's experiments which is trying to create the dark matter, but no success so far. And as I said, like, this dark matter is only this gravitational interaction. So even LIGO, where this gravitational waves observatory is there. So when there were collisions of the black holes or collisions of the neutron stars, it caused ripples in the space-time, and that ripples reached, and we have this detector LIGO which has detected these gravitational waves. So similarly, because we know this dark matter does have gravitational interaction, so LIGO and other labs are also trying to detect any kind of gravitational waves which may be coming from the collision of the dark matter or collision of the dark matter with the normal matter. So a lot of experiments are going on, but so far no success, and that's an important constituent. As I said, like 27% of the mass energy density of the universe is dark matter. Like if you take the mass of our Milky Way, approximate mass of our Milky Way, it is like around 1.5 trillion suns. And out of this 1.5 trillion sun mass, around 1.27 trillion sun mass or 1.26 trillion sun mass is basically the dark matter. And when I say 1.5 trillion suns, that's a huge figure. But yes, the galaxy is also huge. The galaxy is like around 1,05,000 light years across. When I say 1,05,000 light years, that's a huge figure. Light runs at a speed of 3 lakh kilometers per second. Light can take 7.5 rounds around the Earth in 1 second. Like we have a parameter of 40,000 kilometers, and it can take 7.5 rounds around the Earth just in 1 second. Light can go from one end of the sun to the other end of the sun in 4.6 seconds. So that's how fast light runs. Yeah, when I say it can go from one end of the sun to the other diametrically other end of the sun in 4.6 light seconds, that is when there are no obstructions. It is going unimpeded. But that's not what happens in the sun. In the sun, there are tremendous amount of collisions which are happening, and the photons are, these light particles, photons are absorbed, re-emitted, and that happens trillions of time. So basically, it can take even thousands of years for a photon to come out of the sun. The photon which is generated at the core, ideally, if from one end to the other end, it can run in 4.5 seconds. But it can take thousands of years for a photon to come out. It actually takes averagely thousands of years for a photon to come out from the core to the surface because of this tremendous amount of collisions and absorption and re-emission. And then once it is out, then it just takes 8.5 minutes for it to reach Earth. So yeah, basically I just got took a bit digression to explain this thing. But as I said, like out of this 1.5 trillion suns, 1 trillion suns mass, 1.26 trillion suns mass of our galaxy is dark matter. And I'll come to the dark energy now. Dark energy is basically which is responsible for expanding the universe. This dark matter is basically forming these cosmic structures, and the gravitational pull is basically slowing down the universe, right? Because there is a structure, one structure attracting another structure, so that is slowing down the expansion of the universe. Right now, the universe is said to be around like 90 to 100 billion light years across, and that's the observable universe. We don't know if universe is infinite, but that is the observable universe which I'm talking about. So dark energy is like this repulsive gravity. The gravity is attracting things. Dark energy is expanding the universe. It is stretching the space-time. Like when you fill air in a balloon, like all these dots which we can take as galaxies, they are together, they are nearby. And we fill air in the balloon, then yes, they move far apart, right? Then you look at the dots, they are moving far apart as the balloon is expanding. As this balloon is expanding, like same way the universe is stretching, the space stretching, and the galaxies are moving away from each other. And when I talked about the acceleration that the universe is expanding faster, like suppose we take our galaxies here, if you move 3 million light years away, then the galaxy is running away from us, relatively running away from us at around 70 to 74 kilometers per second. The scientists still trying to come to the exact number, but in range of 70 to 74 kilometers per second, it is running away from us. If you look at a galaxy which is then another 3 million light years away, so basically 6 million light years away from us, that is moving at 70 plus 70, like around 140 kilometers per second. So that's how, like every 3 million light years, if we add, the galaxy there is running away in addition of 70 kilometers per second. So 70, 140, 210, 280, that's how, like if you look at from this galaxy to this, 280, then 350, so that's how, that is the relative speed of that galaxy, and it is moving away from us, it is running away from us. And if you take around 4,740 jumps, we'll reach light speed, which is 3 lakh kilometers per second. So if we reach to those galaxies and the galaxies beyond that, then the light is not going to reach us because they are running away from us faster than the speed of the light. So light is not going to reach us. So gradually, if this dark energy is going to keep expanding this universe, there will be island galaxies. The galaxies that we see, all the galaxies that we see today, they'll be slowly running away, and once they reach that 4,000, as I talked about, 4740 jumps, they cross that light speed, relative speed, then they are going to run away from us. The light is not going to reach us. So if the dark energy keeps on expanding the universe, then slowly we'll just have our galaxy. We'll not see any other galaxies, or the galaxies would have gone away. It would just be an island galaxy. And then if dark energy is going to then gradually disintegrate the galaxy also, and then it may disintegrate the solar systems also, and then it may disintegrate the life itself, and which is called the big rip by the scientist, that it may cause the big rip. Take billions or trillions of years, but that is possible if the dark energy keeps on expanding the universe like in that way. If the dark energy becomes dilute, and then the effect of dark matter will be more, it is going to gradually collapse the structures together. It is going to collapse the universe, and that is being called as a big crunch. It's being called as a big crunch by the scientists. So big rip if dark energy wins, big crunch if the dark matter wins. So the fate of the universe will depend upon the balance of this dark matter and dark energy. And about this dark energy also, there are a lot of experiments going on. I'll just quickly discuss about the two experiments. Like there's a Euclid telescope which is going to be launched in 2022 by European Space Energy with help from NASA, and they are going to study the geometry of space. They are going to see how over the billions of years the dark energy has expanded the universe. And we can look at billions of years because we can see the light which is coming from, which was emitted billions of years in the past, and it is now reaching us, right? So this Euclid is going to study the geometry of space, how the dark energy has expanded the universe. And another important experiment is Malay telescope. There in Arizona, there is an attachment now to that telescope called DESI, DESI. And this DESI is basically dark energy spectroscopy instrument. So that is attached to this Malay telescope in Arizona, and it has 5,000 sensors, fiber optic sensors. So it has like 5,000 mini robots, which is looking at 5,000 galaxies at the same time. So these 5,000 fiber optic sensors, or these 5,000 eyes which this DESI has, it is going to look at 5,000 galaxies at the same time. It can study those galaxies in 20 minutes. Then in less than a minute, it can shift to another 20 galaxies. And the plan is to look at around 35 million galaxies. And that study is going to help us to understand the effect of dark energy in these different galaxies. And another experiment is being run at Ayuka Pune by the scientists Ayuka Pune, which is the Astrophysics and Astronomy Lab in Pune. They are also going to study using this large synoptic telescope about this dark energy and dark matter. So these different places, group of scientists are working on it. A lot of effort is going on, but still we don't have a clue about dark energy, about dark matter. And as I said, the balance of this dark matter and dark energy is going to tell us how the universe is going to evolve in future, right? And so the kids who are watching this, there's a lot of opportunity. There's a lot of opportunity to work on it, to work and find out what is this dark matter, what is this dark energy, which is basically evolving this universe, which is responsible for the shape the universe is in right now. And I think if in next 10 years, if the scientists don't find anything about this dark matter, dark energy, then I think artificial intelligence is probably going to give us a clue about it. Like artificial intelligence is already beating Garry Kasparov in chess, is already winning, the AlphaGo has defeated the world champion in Go game. Go is basically a board game, and it requires intuition also along with the intelligence. So the AlphaGo, which is an AI, defeated artificial intelligence, defeated the world champion in Go. Then Jeopardy, which is a language game based on the question answer format, that also defeated the world champion in that game. Then we have AI, which is driving the cars, driverless cars, which we are talking about. Then AI is also doing a lot of ocean exploration. So AI is there in medical field and other fields. A lot of progress is there in field of AI, artificial intelligence. So definitely AI is going to play a role in exploring universe exploration also. So I think if in 10 years, if the scientists don't come up with something on dark matter, dark energy, then AI is going to come up with, going to give us some clue. Or I don't know if God doesn't want us to unravel those mysteries. That is something which is a very core thing of the universe, which God doesn't want us to unravel that mystery. Then maybe it will remain the same way. But yes, the efforts are going on in that direction, and let's see how it goes. So I'll finish it over here, this part 1 session, and as I said, like part 2 session, I'll cover the quantum mechanics. Thank you.